So let's get started. My name is Atte Kettunen, and this presentation is Browser Bug Hunting, Memoirs of a Last Man Standing. And first of all, I want to show you a great example of what kind of love you may be receiving from the vendors if you decide to join our merry family of browser bug hunters. So this is Google Chrome security team troublemaker Chris Evans presenting Last Man Standing rewards in Hack in the Box Kuala Lumpur 2012. These rewards were presented for me and another crazy browser fuzzing Finn Miaubis for our continuous effort in revealing new vulnerabilities from Chrome, regardless of all the effort done by the Chrome security team. Sorry. In this presentation, I have tried to collect all the coolest tips, tricks, and tools I have found in the last 2 years that I've been doing the browser fuzzing. I started in Oulu University Secure Programming Group, aka OSPG, in summer 2011, and there I joined research that was going on browser fuzzing on the open source browsers. And I found my first bug from Chrome in December 2011 from the Chrome PDF reader. And since that first bounty, I have reported around 100 vulnerabilities from Chrome and Firefox. About 60 of those have been reported, and about 40 are with CVEs now. About the bounty programs, there are currently two major bug bounty programs for browsers. There is the Mozilla bounty program for Firefox and Google bounty program for Chrome. There is also the Microsoft Internet Explorer bounty program for 1 month, but I didn't participate in that one, so it's not included in this talk. About the rewards, basically Mozilla has been pretty strict with their policy that only bugs that are regarded as high or critical are with the reward, and that reward is $3,000. These bugs mainly are for the critical memory corruption bugs, where you can have access for remote code execution, and for the severity high bugs, those are mainly disclosure of sensitive information or bugs that cannot be directly exploited, but can be used as help to exploit the browser. From Chrome, things are a little bit more complex. They have base bounty from $1,000 to $3,000 for also sec medium, sec high, and sec critical bugs. And there are also huge amount of different bonus rewards you can get if you prove that the bug is actually exploitable, like showing a vtable control inside the sandbox, or a sandbox escape, or full exploit. You can get countless bonus rewards that then will add up into higher rewards. And also in Chrome, there are a huge amount of third-party libraries that are used into Chrome. And when you find a bug from an open source library, then you will also get an extra reward because it helps the whole community to fix those bugs. So what's so cool about these bounty programs? It is really easy to get started with the browsers. There are a huge amount of different kind of things you can be fuzzing, and there are a huge amount of bugs. And when you get started, even beginner can find the first bugs pretty fast so that you won't lose your interest right away. When you get to your first bounties and first bug reports, the browser security teams, vendor security teams are really supportive and helpful. They try to get you going and finding more bugs instead of trying to get rid of you so that you wouldn't be digging on their products. And there's also the supportive, secretive, competitive community of other bounty hunters that are also fuzzing the browsers. They will help you on some level, but when you are going into too specific details, then it might be that you won't get the help you were actually trying to get. where should you be searching for the bugs? If you're going for use of the freeze, then there is the DOM, CSS, and rendering. Those are full of use of the freeze. For the buffer overflows, there are all the media formats, parsers, and decoders. And also, surprisingly, all the systems use coordinates in any way, like in SVG. I have collected 3 example bugs just to show that it's not rocket science what I'm doing. So this is the first one. It's from Firefox. It has CVE if you want to dig deeper into it. It's basically a global buffer overflow coming from UTF-16 character encoding and escaping. And to find this bug, you should have some specific knowledge about browsers, like using data URIs to have CSS encoded with a chart set. So it's a little more complex. Here's an easier one. Typical use of the free from Chrome rendering. And this is just basic HTML, few styles, nothing complex. And this is the last one. This is really simple. Just need to have a tag, you need to have style property, and have negative pixel value. And you have buffer overflow. So, when you go hunting for a living, I have kind of made up these 3 golden rules because everywhere there is these golden rules for everything. The stay green pops up a few times in this presentation. It's not the military term, not the environmental term, but it's from Chrome. When you go looking for Chrome and Chromium source code, there is staying green chapter over the guide. And it's about staying on the last known good revision of the browser, not going into the trunk version, because the trunk version might be unstable, might have bugs that have already been detected but not yet fixed. So you have to stay on the last good revision of information and of your tools and browsers when you are fuzzing browsers. First main thing are the features of the browsers. If you want to find any bugs, then you have to know what there is to fuzz around. These features, they are all the time changing, and in some times they're really annoying how they are changing. The second rule, if you want to find more bugs, then you have to start looking into the competition, what they are doing, what the other guys are doing, which features they are trying to get into. And this is just to get your resources divided in the right places so that you are not fuzzing the same places where Google, Mozilla, and the other guys are using all their resources. The last rule, still staying green on tools. Because this, when you are trying to make your living out from browser fuzzing, then you have to stay on the state-of-the-art tools to find more bugs all the time. So let's dig a little bit deeper into these rules. The first one, staying green on features. There are new features that are coming all the time. These bring new code, and the new code brings new bugs, of course. There are release notes. There are basic public notes that have all the information, what new features there are. There are also some blog posts that collect more precise information. And there, you have to note that almost every guy who is doing browser fuzzing is also reading the same stuff. So if you're just taking the best picks from the release notes, then you might not be fuzzing best parts where you should be actually going in. There are minor changes that are only in the changelogs and developer forums, where you can find small tweaks they have been doing, like refactoring the code that could lead huge amount of use of the freeze. And also one good place to look new bugs is from old bugs. When you notice that some old bugs have been fixed and the commits that have been, patches that have been fixing those bugs, there are a huge amount of different patches and huge amount of files changed, then it might be that there are new bugs over that area. There is the most annoying part in browsers are the old features that change. Because when you have created your self fuzzer, it's already running, and then someone goes and removes a prefix from the vendor prefix. And that time on, your browser fuzzer is not working anymore. It's just throwing errors or not doing anything actually. And also there's the thing when you go and check the newest release notes, like in Chrome last year, I think, it was MathML. It was enabled in Chrome. I was already going into it, I'm going to fuzz it. And about a week later, it was disabled, and I had a prototype of my fuzzer, but it wouldn't do anything anymore. So that's really annoying. Here's an example why you should stay green on the features. First, on the Firefox Aurora release notes, there's announced that there is now partial support for web audio API in Firefox for web developers for testing. And that was released May 17th. And May 25th on Twitter are already saying that first time in a long time I have more bugs to report than I have time to report actually. I had like 9 bugs at that moment. I have tried to report all those. This was really much work. Daniel Vaditz, he's from Mozilla security team, and he was already fearing for the web audio in Firefox. The second rule, staying green in the competition, this is much harder than the first rule, because some features you can just go and look up for the information. It's all is public for the browsers, all the new features, all the changes, those are public. But with the competition, you can only have small snippets of information now and then. You can try to see what bugs people have been finding. If they have been finding like SVG bugs 10 in a row, you would kind of think that they are fuzzing SVG. And also in these kind of presentations, you can find out what kind of hardware people are using, what features they are fuzzing, and what tools they are using. Like in this presentation, there will be my hardware mentioned and so on. For the tools, you should be looking for what kind of approaches people are using. If they're using like just a command line open file, then you should be looking into if new bugs could be triggered if you just had an HTTP delivering the test case inside an iframe or something like that. In targets, you should be avoiding fields where more people are fuzzing into, because there are few fields where all the vendors are trying to get rid of most common bugs, like in JavaScript DOM manipulation in HTML. And in platforms, different operating systems, of course, have different code on some features, like in audio or in video and graphics. So you might want to go after the graphics driver on Windows, even though someone is already beating up the Linux graphics. For the example, this is on Twitter, Chris Evans, commenting on an idea to fuzz PDF from Chrome without any kind of instrumentation tools. And they are using address sanitizer and 9,000 cores to fuzz the PDF. So it's kind of useless to go with just DMS grabbing and try to find new bugs from a PDF. Second is why I stopped with basic HTML DOM. There are a lot of bugs in a row where like 7 people found the same bug in a small time frame, and it was always Google cluster of us finding it first, then a few other people finding it, then I was like third, and it really gets annoying after a while. And if you noted in here, I in no time went saying that I was fuzzing web audio. So here's kind of, I almost freaked out when I noticed that someone actually told the target I was fuzzing, and I still hadn't reported like half of the bugs I've been finding. So it was, if someone would have just noted that, made his own fuzzer, he might have had time to report those bugs before I had. So it was kind of encouraging that you really try to report all those bugs as soon as possible. The last rule, tools. So the most important is the instrumentation. This has been developing really fast with browsers. When I started in 2011, we were just using basic DMS scraping. If Linux detected that the crash happened, just compared the old DMS for the new one and try to figure out if there was actually any crash. Since then, there have been new instrumentation tools about yearly, and I'm going to present those a little bit more detail later on this presentation. The build environments. I actually stopped building my own versions of the browsers because that really takes most of the time to have your own build system actually working. In some cases, it was for weeks that you couldn't have any updated builds because some of the packages or dependencies were changed, or just you had to update some specific package or update some specific tool to actually be able to build the browser with some specific instrumentation. And those really eat your nerves when you don't know how to fix it. And the problem is sometimes real easy to fix if you just find the actual reason why it's failing. And from fuzzers, people are all the time releasing new fuzzers for browsers. Those mainly are just some fuzzers that have been already used up. So it's just some old version that already had found some bugs. All of those are reported and fixed, and then people release those. You should go through those even though if they are not completely useful for you. There might be some small tricks that you have not figured out previously. Also, those tricks can be gained from another bounty hunters if you just know how to ask the right questions. As an example of this, I have this Chromium startup problem. Chromium just crashed every time you tried to start it up in address sanitizer builds. It was a global buffer overflow in SQLite, and it was just a problem that the Chromium had updated their SQLite, and it was not compatible with the address sanitizer. So it led in that situation, and there was no public information in any forum or any bug reports that how you could fix it. But I managed to find this one reference to a random seer bug from a diff in the changelog of Chromium, and noted that they had added that strict memcomp 0 option to address sanitizer for some reason, tried it out, and it worked. So they had already noted the problem. They had this bypass for it, but they didn't have the information globally distributed. It was kind of problematic. So I'm going to now dig a little bit deeper into the tools we're using. So the first one, the instrumentation tools. The main tool now used for the browser fuzzing by both Google and Mozilla and almost everyone I know who are doing browser fuzzing is using address sanitizer. It is a Glang compiler plugin. It adds just the instrumentation to check memory access at runtime. It is pretty much similar to wall grind, but because the instrumentation goes in build time, the slowdown that's caused by ASN is just 2 times compared when address wall grind can cause like 10 to 40 times slowdown. The address sanitizer was created at Google, and on the bottom there is a link where you can find information how to use address sanitizer with Chrome. I'm not going to add it into here. The address sanitizer itself is awesome with use of the freeze. It's real good with buffer overflows and out-of-bound accesses, and it's good with type confusions, but you cannot actually get any. It's shown randomly as a use of the free, randomly as a buffer overflow, depending what kind of type confusion it is and where it occurs. So it's still detected, but you can't be sure if it's type confusion or is it actually a buffer overflow or use of the free. The RS sanitizer instruments all heap, stack, and global memory, so that it actually catches pretty much every memory corruption bug, at least what I know. I have a few examples from the error sanitizer. Here is an unsymbolized output. So this is the basic output you get at first when a program that is instrumented with error sanitizer crashes. We can see directly the crash type, that is heap use after free. We can see the page inline instruction pointer of the crash, so it's to 9F. We can see that the access was read, and it's located 64 bytes inside a 72-byte region. With this information alone, you can pretty much start to figure out if this is a duplicate or a previous found bug that you have found, or is it a new one completely. Then this output can be symbolized with a Python script that is provided together with Atte Sanitizer. Then you can actually get the symbols of the crash. And at this point, you can pretty easily collect all the information you need to have a database of bugs you have found and try to figure out if the new bugs or new crashes you found are actually duplicates or just same new bugs that you haven't seen before. The second tool, this is the part where I need help. How do you actually pronounce it? I would go with ASAN. That's good enough. So this is a Windows side tool. It tries to mimic the same behavior that ASAN is doing on Linux and OS X. But this is actually applied after a build. So you are using it to instrument DLLs. There were few minor restrictions where you can use ASAN and where you don't. You can, again, have more information from the design documents. At the moment, compared to Atte Sanitizer, ASAN only instruments the heap access. So there is no instrumentation for the globals or the stack. So it misses quite a few bugs. And also, it doesn't in any way report if you find like a null pointer or just a random seg fault. Those won't be reported at all. So it's kind of 50-50 if that's a good pointer or no. Because with ASAN, you have to filter out all the null pointers and all the kind of useless stuff. But with ASAN, you just don't get any of those reports. You are missing a few just basic seg faults, but it's kind of 50-50 situation. But at the moment, I have knowledge that this can be used with Chrome and Chromium. Guys at Mozilla are trying to get it working with Firefox, but at the moment, I don't have information if they have actually managed to do that so far. This ASAN causes 3 times slowdown, so it's a little bit slower than ASAN, but still quite fast. This is the basic output from ASAN without any instrumentation. So again, we have the same information as with ASAN. We get the crash type. We get that it was read of size 8, and we have the page inline instruction pointer. But the difference with ASAN and normal ASAN is the actual symbolization of the outputs, because you cannot directly symbolize the output from the console. You have to set the instrumentation tool to actually dump you a crash dump that you have then analyzed with the, again, Python script that uses, if I remember correctly, Windows debugger to symbolize the crash. But you get same type of information as with ASAN. Again, crash type, access type, size, and the location. And also you get the crash tag, shows you the symbols. And with this, you can collect the information you need to detect if the bug is actually a duplicate. The last instrumentation tool I have is page heap. It is Windows built-in heap allocation monitoring. This is kind of now obsolete on my system. I'm not using it anymore after I switched into ASAN. The problem with page heap was that it kind of works with Chrome and Chromium. The problem is that page heap messes up with the page alignments. And in some places of Chrome, you can use that Chrome allocator environmental variable to, when you set it in the Win heap, you can get the specific allocator for the Win heap and page heap. But that doesn't affect all third-party libraries. So if you're fuzzing like VO files, then you most probably start to get almost instantly crashes that are coming from FFmpeg and are because of aligned frees that are used inside. So they are not actually bugs, but it's more that they are using an allocator that doesn't support the page heap. In Chrome, the page heap doesn't give you any feedback. It just causes a crash when an application does an access violation. And in Chrome, you can get mini dumps if you enable Chrome error reporting so that all the statistics and logs are sent automatically to Google. So you want to firewall Chrome or just cut the whole internet connection because you are sending all your 0 days and all the analysis over to Google at the same time your browser crashes. That's not a good idea. And you should be using debugging tools 32-bit version for some reason. I'm not quite sure why that is. But with 64-bit version, you just don't get any crashes. That's the only thing I've noted. Here's an example of Chrome mini-dump analysis. I had to truncate it a little bit to get it fit in here. But you can use the Chromium symbol servers to have the actual symbols on Windows. And again, you can in here get the symbols where the crash happened. You can get the type of the access violation. But you get only the information that it was access violation. You don't get the specific crash type if it was use of the free or buffer overflow or something else. Next to fuzzers. So downfuzzing still works. And even this year, like a few months ago, a bug was found with just bit flipping audio files. So it's still there. You can still just use dumb fuzzers. And you don't need any black magic to actually find those bugs. And smart fuzzing, it's awesome. Pretty fast build up a small fuzzer to fuzz some specific area, like in JavaScript specific API. But those normally just, you find huge amount of bugs and it's out. And there might be a few regressions later on, but it's still almost empty at that point. And downfuzzing, most of the guys are using Radamsa. I'm trying to now push Surku. It's a tool I wrote, so it's much better than Radamsa, of course. Both of those tools are from OSPG, and those are the main tools that are now used in kind of general downfuzzing in browsers. One of the cool tricks in browser fuzzing is to use just old repro files. So you have these crash tests, layout tests, and so on in the browser source code when you pull the whole source code. And you just can find all the files that have crash tests in them, copy them into some directory, then run Radamsa over it, and then just push the output for the browser and see if something crashes. And it's quite normal that you actually find like corner cases where buffer overflow was fixed on the upper corner, but there are still negative values that trigger the same condition or just cause the buffer to underflow. Smart fuzzing, this is mostly the stuff I'm doing nowadays. So I just take a random specification that looks like cool, and there are not many bugs reported on it. I just take it, start to read it through, how it looks like. If there is something cool that looks like there could be bugs in it, then I just build a small fuzzer for it, start looking if there are any bugs. Here the most important part is to stay green in many levels, because there are the actual specifications that are developed in different ways that the browsers are actually implementing those. And in some cases, the browser vendors are implementing the features that are later on removed or changed. Like in web audio, they have changed about all the meta names in some points. So you have to be careful when you are developing the fuzzer. if there are a change, you have to go through your whole fuzzer if there is that feature used and if the change affects it. The cool part is that most of the APIs are really similar, so you can just build a one fuzzer, build it generic enough, and after that you have to just copy paste the stuff from the actual specification, and you have a new fuzzer. And I have been using that specification plus grep plus sed equals $. So here's an example I extracted from WebAudio API specification. You can pretty easily see that it's interface for Panner node. It has 3 methods, which all take in 3 tuples. And there are 3 attributes, all doubles. This is from a Canvas API. It's about the same, but the methods have 4 doubles in them, and the attributes are unrestricted tuples. So it's basically, if you just have one script that does the grep, sed, and then outputs into a file, then you can pretty easily have both of these parsed with the same script and can build your fuzzer out from that. Hardware. So I'm all in for physical machines. Sysadmining is fun. And for some reason, there are not many people who are doing browser fuzzing with virtual machines. The problems I have been facing with them is that they are sometimes unstable. And if you are fuzzing anything that is related to hardware or going deeper level on the operating system, you can get huge amount of crashes that are actually just because of the virtual machine, not actually because of the browser. You want to use SSDs. With the address sanitizer and SiSi ASAN, you need to have a lot of RAM. Normally, you can end up with the browser instance eating up like 4 to 10 gigabytes of RAM. And if you are thinking that you shouldn't be starting the browser fuzzing because you have like one laptop at home, there is this vicious cycle I have been going through. I find a bug, report it, get a bounty, buy a new computer, because of course with more computers I can find more bugs. Then I find more bugs, then I get more bounties and buy more computers. So I have ended up like with 14 computers or something like that. This is which we started in 2011 when I started in OSPG. We had 2,000 euros hardware budget, which would have as kind of versatile fuzzing cluster as we could. So it's that. And the only thing that was cool with those machines was that the operating system was on a USB stick. So it just made a new USB stick, and you could switch the target or you could switch the browser just by flipping different USB stick in, reboot the machine, go on fuzzing, then build a new stick, tomorrow flip it. From that, we have ended up with this. So we have like 6 new machines, 6 those dual core AMD Antique server machines. I still don't know where those came from. We have own devices that have been bought with bounty money. And this is the office now. There are still the patches, if you notice on the left upper corner. There is 5 of them still alive. And I counted this at home. There is like 15 or 16 machines on this picture. But what did we actually achieve with this? We reported over 90 bucks. Well, it's more like 200, but there was no cool meme for it. So it's over 90. This is the monster we are fighting with. So it's cluster of us. It's the Google fuzzing cluster that 2012 was already using 6,000 Chrome instances per hour, running through 50 million test cases per day. They had plans for quadrupling at that time. No one knows how many machines they are using now, but at some point, Chris Evans was talking that they're fuzzing PDF with 9,000 cores. And with that, you add the other features they are fuzzing. Must be huge. They're using mainly ASAM. Now they're also using SciSci ASAM. They have multiple different modules they are using to fuzz the different features. Automatic minimizations, regression range verifies if the fixes actually fix the problem and cause huge amount of duplicates about this. And that code I have added at the bottom is actually from Chrome issue tracker on one bug, where a guy was tanking cluster fuzz for minimized test case and full report on the issue. And it was later on said that cluster fuzz is a soulless bug hunting machine. It has no want or need for your gratitude. It lives only to feed on bugs. So it's awful. So what I have been doing, I now have 14 machines. That's still saying 12. They're running 24/7, about 50 cores, a little bit more RAM than that. Approximation was for 20 million test cases per day, but it depends on what file formats they are actually going in, because there are 19 different file formats going on all the time, and it's randomly picked which formats are in what time running. So it varies between, I have seen as low as 5 million going into 40 million test cases, so it's pretty good. The whole system is built on JIT, SCP, and few scripts that do the automatic updation of the browsers and the fuzzers, and the automatic minimization of test cases, and almost writes the full report so that I only have to copy paste it on the bug reporter and it's done. And fuzzers, I'm using Radamsa and NodeFuzz. This is a tool I have created myself. It's a browser fuzzer harness where all the test case generators and instrumentations are divided into modules. So you can switch between operating systems, and you can just switch between different instrumentations just by running with a different command line arguments, and that is it. Also, you can have multiple different test case generators running at the same time, so they just randomly select which test cases are fed in which time. For the test case input, I have used WebSockets, because that allows two-way communication between the browser and the fuzzer. So you can actually deliver information if you want to have like even smarter module that actually tracks if the files go through, or if you want to have more statistics from the browser and for your fuzzer. You can have the stable and a trunkish version. The trunkish version is not the real trunk, because the real trunk is like broken all the time. You just fix it enough to get it into the trunkish repository and then break it again. I added a small setup script if you want to try it. It works on Ubuntu, at least for 12.04. You have to have Google Chrome installed before. Just run those commands and it should run automatically. If you want, you can go into the config JS file to manipulate it even further if you want to have your own instrumentation and so on. So for the demo, today I have selected the web audio module. It's the newest one that have been really finding more bugs than just a few. It is a fairly new API. It was built into Chrome in 2011, and in the Firefox it was the 17th of May or something like that. The green parts are what I thought when I started reading through the API. So the first was modular routing, sounds like use of the free. Then it was basic audio operations performed by audio nodes linked together to form audio routing graphs. It just screams that there are bugs in it. The next one was the several sources inside same context, different channel layouts. It's almost automatically use of the free. And the great flexibility and creation of complex audio functions, sounds like a buffer overflow. And in the end, I found that many bugs. It's actually now like Chrome, it's like 7 use of the frees and 5 buffer overflows or something like that. Firefox, it's like 2 and 9 or 2 and 10. And that's, by the way, my new car I got after I made this module. So here's one bug from the web audio. This is from Chrome buffer overflow. In this point, my fuzzer has had like 50 lines of code. It supported creation of the audio context and 2 different audio nodes, oscillator and gain. And you didn't even need the gain to find the first bug. So you only would have needed to have the context creation and oscillator. This is from later on. This is use of the free. Now there is some dynamics in it. It tracks which object it have created and so on. I'll now have the demo running. So I'm running the web audio module. This is basic output from it. So in the beginning, we have the creation of the different audio objects. And then later on, we just have basic methods and basic attribute changes. So I'm running it on 2 instances on parallel. Hopefully this machine won't crash in it. The upper one is for Chrome. It's Chromium 26. The current version is 28 or 29. So it's a little bit older because on Chrome, they have fixed all the bugs. So I, of course, selected the version where all the bugs still exists. And also for the Firefox, this is from June, this version, so that there are more bugs in it. So you just see how many test cases there are going, what size those are. When you see symbolizing text, then we have found actually a crash, and it's analyzing it on the background. We can see the browser going on over there. And we can see that there is already 2 bugs found. First one was a heap buffer overflow from Chrome. Okay, there are also use of the free now. So 2 bugs from Chrome, 57 test cases going. Firefox, stack buffer overflow, and null pointer from out of memory. And I'll leave it running so you can see how many bugs it actually finds during the questions. So if any of you have any questions, I can answer it now.
So what's the test case minimization procedure? You mentioned the script, but...
Yeah, it's fairly crude. I only have it like really working on the test cases I generate on my own modules. So like the one I showed with the web audio. It basically goes from the bottom to top of the file, removing 1 line of code on all rounds, then tries to feed it on the browser, checks if it still crashes. If it's not crashing anymore, recovers the line, and then moves on the next one. Go few passes, then start to remove empty functions, empty objects, and so on. And in the end, you have some sort of test case. That's not working if you have, if you are like downloading random samples from the internet. It doesn't work as well as it should work, because in some cases those files are constructed really weirdly or generated by machine. So you cannot actually go just removing 1 line at a time. But it works in most cases. Any other questions?
What is your average test case size and how far can you then minimize it down to?
So the question was that what is the average test case size and how small it can be minimized automatically. So normally, like you are seeing in here, it's like from 5 to 20 kilobytes each. Normally, I'm running a little bit bigger files, but it's a laptop running 2 instances of NodeFuzz, so it cannot handle it. It starts to time out after if I increase the line count over like 400 or so. And normally it's around 40 kilobytes or a little bit over it. And normally it goes down into a few hundred bytes overall. And in some cases, there are, of course, test cases where you have to have huge amounts of startup code just to get all the objects set and so on. And then you have the 2 code lines that actually trigger the crash. And you could minimize the whole thing in one blob of JavaScript that would be like a one-liner. But it looks awful, and they can actually understand how it works in the Chrome team. So I have been just minimizing it around 1 kilobyte is a good size. Then they won't be complaining that it has too much stuff in it. So the second question.
Hello. My question is about timelines. So what is the normal timeline for you from point of discovery to declaration to the vendors? And the second part is, what about when the vendors know that there are bugs you've reported to actually creating a patch? Do you have any views on the timelines?
Well, I check my cluster like daily. So if I find a bug, I'm reporting it within 2 days from it. From that, it normally takes from 1 to 2 days for the vendor to start fixing it. They are in that point going through how the actual case file works and what is happening over there. And depending on the severity of the issue and how complex the patch is, it is sometimes these bugs are fixed in like 4 days from the point where I reported it. But in some cases it takes longer. Of course, there are some bugs that need rewriting of whole classes and so on. So those take a little bit longer. But normally it's not so many days. But actually the patch to be launched, the browser vendors have the 6-week period where they are releasing the new version. And normally they try to get all severity high and critical bugs fixed before the next new version release. And so in the worst case, it takes the 6 weeks, basically. In some cases, it can be that they push the fix of a lower severity bug into the next version. Normally the 6 weeks, it's the maximum. Normally it's shorter. Any other questions?
I was just looking at the test cases for Firefox seem to be sort of outpacing Chrome. Is that just an efficiency thing with your script in Chrome, or do you find that there's some additional return on investment in one browser over the other?
The implementation of the web audio in Chrome is much more wider than in Firefox. In Firefox, it's just a version for developers for testing, and it's still missing quite a few of the features. And Chrome is, I'm not quite sure if it's implementing the whole API, but at least almost the whole API. So my fuzzer is generating all the objects and all the methods that are in the whole API. So that will cause Chrome to do more work than Firefox. I haven't actually benchmarked if there is any difference between these browsers in web audio.
So sorry, just to follow up on that then, in terms of going after more bugs or trying to obviously then get more, paid out more bugs in less amount of time, if you did try and benchmark it and you saw that there was more efficiency in one browser over the other, would you then try and focus more on that browser in order to try and get more out of it?
Well, technically, Firefox is paying 3 times the sum that Chrome is paying. So basic inside the sandbox use of the free buffer overflow pays $1,000 on Chrome. And Firefox, it's almost automatically 3,000. So that pretty much covers the efficiency. But of course, I have been doing more testing on Chrome because in most parts, Chrome is faster than Firefox. And Firefox is a little bit harder to handle in some cases when you're doing your testing. There is a few cases where my whole fuzzer just stops with Firefox, just not restarting the browser anymore. And that's also one reason I'm a little bit lowering the usage of Firefox and going for Chrome. Any other questions?
All your bugs are bugs found by fuzzing, or do you do like source code audits and other reviews?
I'm only doing fuzzing. I don't touch the source code even with a long stick. It's not my field. So did you have?
Yeah. Do you, just from the fuzzing work that you did, do you have any views on which browser is more secure or less secure?
Every time the same question when I open my mouth and say unlimited browser fuzzing. No, I have no idea. There are fewer bugs on Firefox, but that automatically on Firefox, if it's a more severe bug, it automatically goes to exploitable. Instead, in Chrome, most of the bugs are inside the sandbox, but there are more bugs. So who figures if those are exploitable? Any other questions? There's one going.
You didn't mention Safari, Explorer, Midori, all of them.
I haven't touched any of the non-bounty program browsers, except we have been fuzzing Dillo on our office. There are few bugs in it, not many. It was just kind of side project. On one case, I have implemented Node fuzz instrumentation on Internet Explorer, have run it with it. There are a lot of soft bugs, but I didn't want to report those because it was kind of hard to try to figure out if those were actually kind of real bugs. And in Chrome, I can just ask from the security team guys if they think it's worth reporting, and I didn't have any Microsoft contacts, so I didn't start to look into deeper on those bugs. There were so many different kind of null pointers with an offset and so on. It's just so overwhelming at the start. The overall, I'm only focusing on the browsers that have bounty program. But the tools are usable against any open source browser that ASAN and, well, SciSci ASAN is a little bit problematic if it's not even working with Firefox. But ASAN is usable on all open source browsers and almost all open source applications. So it should work, and I think almost all browsers implement WebSockets, so NodeFuzz would directly be useful with other browsers also. Any other questions? Okay, so thank you.